everyone, and today we are going to have a discussion on how to use DAMs for dam simulations. These DAM for reserve, or we can call as reservoir simulation, and how these dams which we simulate can be used in groundwater hydrology. Because nowadays you know that especially in hard rock part of India, water is a big problem, especially in the summer months, say April, May, June, and in some areas even in July month. So, how to augment groundwater using this rainwater, that can really this simulation can help decision makers to make appropriate decisions. And recently in different states have started some projects just to augment groundwater and also rejuvenation of various streams. Like in Uttarakhand, they are also doing a rejuvenation of Rispana river, which is not perennial, ephemeral channel which passes through Dehradun. Also we understand that similar kinds of projects are being planned in Andhra Pradesh, and in earlier several such projects have been done by some non-government organizations in Rajasthan also. So what is happening that we are having almost sufficient rainfall or precipitation in total 1 year, but most of the majority of that water which is coming on the surface of the earth in form of rainfall or precipitation is going as a waste, as a surface runoff into either Arabian Sea or Bay of Bengal. Now, say for example about roughly 95% of total water is going as a waste. So, if we start just recharging our groundwater regimes using this water maybe of 1 or 2%, then I am sure for at least for a decade we should be able to solve the water supply problem in the country. And this applications of DMs and dam simulations will really help. So, this is what we are going to discuss, the application part as well. This dam simulation we have seen through a demonstration also, but very briefly I will touch here and then we will discuss about this ground. As you will see that the main input in dam simulation is a digital elevation model. That topographic surface will help us to find out various options or various scenarios along a channel or in a watershed or a basin. For example, here what we are observing that there is a watershed, and in blue color the streams are also showing, and these streams have been derived from surface hydrologic modeling, and then a line has been drawn to indicate that here the dam or a reservoir axis would be there, like of this much length. Now, the height of this dam axis we can decide once we start getting this topographic profile. So, like in GIS softwares, as soon as you draw a line, you can get a topographic profile like this. So, that means in this part I can fill with water and can create a dam in a upstream or a reservoir in the upstream, inundate the water. So, by looking this topographic profile, I can fill with water. Like here, this topographic profile, once I choose that I want the water level of this meter, that is 1400 meter in this case, this is going to be the inundated area in the upstream. Now, reservoir has been simulated very easily. You can also get lot of other data sets like location, length, position and angle of dam. These can also be changes. So, if my requirements are not getting fulfilled or I am overestimating or unnecessarily constructing a large reservoir, I can either reduce the height of the reservoir or can go upstream. And if I want more water, then probably I can come to this part and can create another reservoir having more storage of water. So, that means I can play with my system and can create the different kinds of reservoirs or different scenarios which decision makers will make the appropriate decision. Sometimes when we ourselves are decision makers, then still no problem, we can do it this part also. So, here what we are seeing, that even if I change the height of dam, the size will change accordingly, especially the inundated area. So, on the right side what you are seeing a topographic profile, that is the plan the section view or profile view, and here you are seeing the reservoir in a plan, in a 2D. So, everything becomes very clear with simple simulations like this. Now, of course, as I just mentioned, that many other parameters which are required to decide or to go for an appropriate decision or optimum decision, then I need what is going to be the volume, what is going to be the area and perimeter of this reservoir. That too can be done. If I do not have GIS or digital elevation model, I tell you with topographic maps, it is near impossible to estimate such things very accurately. So, what people have been doing, they were using just contour line and deciding based on that reservoir. But if I change the location or rotate my dam axis, then again it has to be calculated. But here things becomes quite fast and very accurate as well. Now, about this profile, the profile which you are seeing, a topographic profile, lot of many parameters can also be derived here. Important point is the like horizontal distance and terrain length. Horizontal distance is this length which is the top of the water surface. Of course, it is in 2D. Recall the discussion when we had about this perimeter or planimetric length and our terrain length. So, similarly here the horizontal length is the planimetry length and the terrain length is this one, which is this one. So, obviously terrain length will always be more than your perimeter length. Same would be also with the perimeter also. Now, these will have two different, like here wetted perimeter. So, wetted perimeter is the part of the water body which will touch the surface or the ground, that is perimeter, not the perimeter of this polygon which you are seeing on the left image. So, this all parameters which are required for a civil engineer to decide or design a dam or a reservoir can be extracted from this exercise, that is dam simulation, employing a digital elevation model in a GIS. Similarly, if I change the position, earlier I had like 1400, if I now what I have done, here I have shifted the dam axis. In my earlier picture, if you recall, dam was here. Now I have shifted the dam and rotated the dam axis. I am again getting some new values, new locations, everything new. So, if out of these two options which one is better, decisions can be taken before really anything happens on the ground. And that is the ultimate purpose of GIS, that is the modeling. Recall the definition of GIS, what it says, that is a computer based information system will store and retrieve, analyze data which is coming from variety of sources and model as per user defined specification. So, here user is providing all these details, that location of dam, height of the dam, and then the modeling is being done. And ultimate aim of the model is to predict something which has not happened on the ground, but before that we want to do it. So, this is what this platform will allow you, and by this dam simulation you can do lot of such things. So, once I change the location of reservoir, height I have kept the same, obviously other parameters, that is the volume calculations or profile characteristics, will also change. Doesn't matter, I can store as a separate, and whenever there, suppose I had a target of a certain amount of volume of water which I want to store in reservoir. So, if I achieve that one, fantastic. If I do not, I will go back again, shift my reservoir maybe to the downstream, because if you go towards downstream you can store more water, but if I go to upstream then catchment area will reduce. So, that judgment should also be made. Now, this is the point which I was just touching in the beginning, that the water which we require is very little or part of the total water which is available to us. See, 96.5% of the water is available in ocean, and but that is saline, and fresh water is just 2.5%. Out of this 2.5%, 30% is the groundwater, which generally we take out and use for drinking, irrigation or whatever. Glaciers and ice caps, which holds about 68% or 69% of total water. And then out of this, of the surface water or the fresh water 1.2, this is how it is stored, that lakes stores about 21%, the ground and ice permafrost about 69%, river water is just 0.49, because most of the water during monsoon time, say in India, is going as a waste and does not stay in the river. But of course, this is the data for the world. So, almost the same scenario in India also. So, that means because the groundwater is an issue, lot of water is going as waste. So, we need to store the water, delay the runoff even for a few weeks or months, and if we do it, we can recharge the groundwater regime, and you know the groundwater will be available for round the year rather than surface water. Because surface water, there are other issues like loss to the atmosphere in form of evaporation and can become easily polluted. And you know, this turbidity and sediments, these are another problems. But if we store water in form of surface water only for some time, may not be round the year, then we can solve lot of problems of India in groundwater. Now, if we see that 54% of the India faces high or extremely high water stress. So, except for northeast and some parts of J&K or some parts of Andhra Pradesh and Odisha, remaining parts are really having big problems. And if we see that same percent, 54% of India's groundwater wells are decreasing. So, because we are exploiting more water, very interesting figure I want to share with you, that the average rainfall over India is about 1120 millimeter per year. And if we calculate the total volume of water falling over India in 1 year in form of precipitation, in last 100 years or more, it has remained same. That means the rainfall which is or precipitation which have been occurring 100 years back, it is almost same. The only thing, at that time we had the population of 35 crores like, and now we are having 135 crores. At the time of independence, that was the situation. So, from 35 crores from 1947 in 2020, we are having 135 crores. But the augmentation, rainfall input has not changed, only the output, over exploitation of water. And that problem, as I have been saying, further I will add that this problem can be solved in 1 or 2 years time if we start storing even 1% of extra water of rainfall for the domestic requirements. At least drinking water problem can be solved. But if we add 2 or 3% of total rainfall goes as in groundwater, then irrigation and industrial requirements can also be solved, at least for a decade or so. But if population keep rising like this, then we have to create this one maybe 10% of total rainfall rather than just 2-3%. So now annual total that average annual precipitation over India which I was mentioning have remained constant, almost constant in last more than 100 years, which is about 4,000 cubic kilometer total. And groundwater recharge is just 433 cubic kilometer, and rest is going as a waste. You are having surface runoff, maximum part is going as surface runoff. It does not store. Now I will give you this all idea how to do it, how to solve this problem through a case history or a study which we did few years back. If you see in this figure, you would find that there are 3 or 4 reservoirs. 2 are big, 2 are very tiny relatively. One is here Narain reservoir, another one is the Sironj river. There is another small reservoirs are also here. And this is hard rock terrain of central India, Bundelkhand region. In the basement you are having gneiss, Bundelkhand gneissic rocks or granite if you wish to call, and on the margins you are having Deccan traps or basaltic rocks. Like here you are having basaltic rocks in this part, and in this part you are having weathered basalt, and of course you are having thin soil and that thing. But the point which I wanted to, or the things which I wanted to show you, that see these reservoirs, this is a Indian remote sensing satellite image, IRS list 3 image, and it is a false color composite, and therefore the vegetation is appearing as in red color, because infrared channel which is having the maximum reflection has been assigned a red color. So what you would see that that there is a reservoir, and in downstream I am having a area, influencing area, or I call the benefit area. There is a reservoir, this blue color one, and then I am having a benefit area like this. But the interesting part, the reservoir which is having larger inundated area having less benefit area as compared to the reservoir which is having the small inundated area. So what could be the reason? Because by analyzing satellite images, interpreting satellite images, we are developing a knowledge about local groundwater regime or local knowledge if I want. Since in these areas you do not have any reservoirs, and therefore there is not such growth of vegetation as we are seeing in the other parts. So in future if we want that these areas should also become green or in false color composite red, then what do you need? You need similar kind of reservoirs along this area as well, across these valleys or alluvial fills. These are all ephemeral channels and which have been blocked, the rainwater has been stopped, and then you are getting groundwater regime, because it is there is no lift irrigation, there is no canal irrigation or any other thing, simple reservoirs, and they are recharging groundwater regimes. Farmers are exploiting that water and putting in their fields to get the crops. This is February image. Now if you see that this blue colored reservoir, though in size is small, but it is located on relatively on higher grounds as compared to this Narain reservoir. And because of there is a elevation difference, that means this reservoir is providing better hydraulic gradient as compared to Narain, which is almost in the same level. So if we want to make this area more green, then what we need to do, we have to learn from Sironj reservoir location and construct reservoirs on little higher grounds. Though we will lose little, we will have a less size of catchment of watershed for these reservoirs, but nonetheless they will provide better hydraulic gradient and better groundwater recharge. Otherwise, geology wise, all these the entire area is same, that on this side you are having Deccan traps and on this side you are having granite. Of course, there are some soils and developed, and along which agriculture is taking place. So there are many such reservoirs in this area. So if I cover a larger area. Those Sironj and this other reservoirs are still here, which you can see. Narayan Reservoir and Sironj Reservoir. But I am covering now a large area because it will carry some important things. If I see a digital elevation model, it looks like this for that area. So, implying GIS, we can, and giving weightage to different themes or different layers, like for example, geology, soil, geomorphology, water level, or changes in water table between pre-monsoon and post-monsoon, and using this groundwater yield of different rocks. A similar kind of maps for any hard rock terrain can be prepared, which are groundwater prospective zones. That means if anybody is looking for a well or siting a well, then these red areas are the best suitable. And whereas if you go in the Deccan Trap areas, these are the areas where these are not suitable at all. So, very poor and poor color are those areas which I was saying about the basaltic rocks. Rest of the areas are either moderate or good chances of getting water. So, these alluvial fields along the these ephemeral channels are good to get the water. There are high chances. Similarly, using again and little different techniques with different weightages, we can also develop maps for any area in the country, which is the potential zones for future reservoir sites, in order to recharge the groundwater regime. Again, the dam simulation will come here directly. So, these are the areas, the black one are the one which are the most suitable, not at the same level, but little higher, and not too much higher that therefore the water set becomes small. So, just at the edge of those higher grounds, if we because we have learned through that blue reservoir or Sironj reservoir that if it is located on higher grounds, it will have large benefit area relative to submerged area. So, that knowledge we developed, and based on that knowledge we can develop such maps. These are nothing but the modeling, GIS based modeling, getting information, arranging the information, putting in different layers, giving the weightage, and finally coming with two. So, two outputs I have shown. One is the prospective zone, groundwater prospective zones, and another one is the groundwater recharge and structures locations, where you should locate. Now, the weightage which we have assigned to different layers or different categories within one layer can be different in different areas. So, each area has to be studied first through satellite images, getting some other data sets, preparing such things, and then you can do it. The biggest advantage you can take of already existing reservoirs and studying them, that what is the submerged area, what is the benefit area, and then you design your weights for different themes. Now, we are still in the same area and exploiting something else. Here you can see lot of small reservoirs are there. Just to locate, this is the Betwa river which is going something like this, and will meet the Chambal, and then Chambal meets Yamuna, Yamuna meets Ganges. Now, these white lines which you are observing here, these are the quartz reefs. These are geological structures which are already present and which are serving as a dam axis, very long dam axis. So, people in past have exploited these quartz reefs and can created or could create small reservoirs. Some might be even natural one. And wherever you do not have such quartz reefs and inundation of water like in this part, you do not see vegetation. This is again false color composite image. So, what we are learning basically that if there is even in a hard rock terrain, if we inundate water for some time, it will recharge groundwater regime in the surrounding, whatever the geological conditions are there. And ultimately there will be growth of vegetation as you are seeing also in this image. So, wherever you are having water in that vicinity of water, you are having growth of vegetation, and wherever you do not have any water body, you do not have growth of vegetation. If I take individual reservoirs, you can see that, see, this is the quartz reef which is going something like this, northeast southwest direction, and this is the downslope side. Along the reservoir in the upstream area, especially in the perimeter of the reservoir, and in the downstream area, you are having a benefit area. Likewise, another example, and here what you are seeing in 4 directions, the water is available in form of groundwater, and farmers are exploiting to put on their fields, and that one is in the northwest southeast, another one is northeast southwest direction, because these are the geological structures which are controlling. This northeast southwest is generally the trend of these quartz reefs, and whereas northwest southeast are the geological dikes which are present there. So, only along there is a maximum movement of water, otherwise in other part there is no harm. Because remember the early discussion what I mentioned, that there is a quite sufficient rain precipitation over India. The only thing we should delay the runoff as much as possible. If we do it by few months, it will recharge the groundwater reserve. Few more examples are here. One more example is here. And here I would like to spend some time, because this is my hometown in Uttar Pradesh. And this reservoir was constructed more than 60 years back. And at that time, the population of this town was roughly 35,000. And since then, because of siltation and encroachment, the size of the reservoir has reduced. That means the capacity of holding water has also reduced. But the population in the downstream of reservoir has increased by manifold. So, earlier we used to get 24 hours water in our taps. Now we do not get even for 24 minutes. But recall again, the input which is coming in form of precipitation over India remained same. Only our management has got poor. We did not augment in the same way as we added to the population. Nothing lost. Still, if we start doing this thing, in 2-3 years time we can solve this problem. How we can do it? We can quantify things also, because many decision makers, they love the quantities rather than qualitative assessment. So, that can also be introduced by taking a ratio, that is benefit versus submerged ratio, and this index can be used. So, what we did, we took 21 reservoirs of that Bundelkhand area and calculated this benefit versus submerged ratio, which is on the rightmost column. And as you can see that sometimes you are getting 28.18 ratio. That means if I sum in this particular area where currently this reservoir is there, the Chanderi one, if I submerge 1 square kilometer of area in the vicinity of this reservoir, there are chances that I will get 28 times return in form of benefit area. It is a wonderful scheme. However, there are locations where this ratio is less than 1, 0.66. That means these are the not areas which I should put my investment of land. But if we decide that my threshold is say 10, I need at least 10% return in form of benefit area. That means again I will repeat that if I submerge 1 square kilometer of land, I should get in return at least 10 square kilometer of benefit area. That means about more than half of the area can give us return in terms of groundwater recharge by 10 times in terms of land. Important thing is that reservoirs or dam access has already been created by the nature in the form of quartz reefs. So, we have to identify only those areas where a stream is breaching these quartz reefs and is still unchecked. So, if we block that stream, create a earthen dam, a small earthen dam, we will delay the runoff, we will start recharging groundwater regime. And as I have been saying that that if we start doing this thing today, in 2 years time in that particular area, this problem can be solved to large extent. And as you know that satellite images provides unbiased recordings of the things. Here what in this example what we are seeing, though is a larger reservoir which is also called Rani Lakshmi Bai reservoir, it is locally it is known as Rajghat. So this was started just filling in 2001. The entire project was not completed at that time. Next year, that in 2002 started to its maximum height. If you notice that these are the true color images from a MODIS sensor, and what you would see that in 2001 hardly there was a growth of vegetation. Here you have started seeing greenery in 2002. Remember, just in 1 year. If you go in the third year or 3 years after that, you would realize that the entire area has almost become green. So compare this 2001 with 2004, you will get the answer that how many years it would take to recharge groundwater regime in a hard rock terrain like Bundelkhand area. Just 2 years. After 2 years, as you can see, a large area is getting benefit because of this reservoir. So when I was showing this to and in some meeting, this particular image or set of image, series of these time series images, people said that for 2001 you might have taken a pre-monsoon image, and for 2004 you have taken a post-monsoon image, and then you are showing the differences. I said, don't worry, as I have said, the satellite images records unbiasedly. So this is all 17 Decembers of different years. And as you can realize that this was just 1 year after the reservoir filling, you see the greenery here and in this part also. And slowly in just in 2013, this is the area has become green. There is another evidence of this, that the local these these mandis or a local where the farmers bring their grains for selling, a wholesale market. When this reservoir became in existence and started recharging groundwater regime, in the next year the local mandis or these wholesale grain markets could not handle that kind of output, because there were the land was there, soil was there, the only problem was water. As soon as water started coming to the farmers in their wells or through canals, the crop after crops started coming. That means if we recharge a groundwater regime, even for few months, weeks, it will have effects in downstream or in the vicinity. One more example from the same reservoir. This was the year 1990 from Landsat MSS image. This reservoir was just, this project was taking shape, and see what happens. This is 2002. A large area became green. This is again true color images. So a reservoir, doesn't matter even if it is small or large, will recharge the groundwater regime, particularly in hard rock terrain. And the benefits in the downstream or in the vicinity will start coming in 2 or 3 years time. And this is the joy of water in the area where these people did not have water and sufficient rain was there. And see, these are unlined canals. And what is happening, because of unlining of these canals, whenever there is a water, they too recharge the groundwater regime. So even if for 1 month there is a water in these canals will recharge the groundwater regime, and your groundwater is getting enriched. So we can solve this problem for a large central part of India, just exploiting these quartz reefs which are running northeast southwest. And a large area was studied, and we delineated these quartz reefs like this, red which are marked here, there are some of them are running for hundreds of kilometers. See the scale here, 50 kilometers. So, like this one, roughly it is running for 80-90 kilometers, and this is the general orientation of all these quartz reefs. So, what basically, this is how in a zoom part in satellite images these looks. A stream is going unchecked. So, if we block using local materials, we can create a reservoir, a small reservoir, not multi-purpose, not for hydropower, only for the groundwater recharge. And the dam simulation which we started can be done here at this stage to convince people that this is what is going to happen. So, if you go on the ground, this is how you see these quartz reefs. Having this dam natural, this is all natural, and dam, the height here is 25 to 30 meter. So, these abutments can be used to create a reservoir. So, this is what we simulated and then predicted that one, that these are the areas in that locality, these red one which are marked here are sites for potential reservoir sites and especially for groundwater recharge. One is like this, the quartz reefs is going like this. So, if we block this one, a stream is going like this and coming like this, it will create a reservoir, and we can simulate like this, which we have done. In the background, it is shaded relief model for the same area, and the blue color is showing the inundated area. Now, there will be other things which we can achieve implying further or do the analysis in GIS. So, we can change the height. Of course, if we want to exploit the quartz reefs, then we cannot change the location, only the height we can change, does not matter, but still we would be able to inundate the area. This is how it looks more, if we see closely in the ground, this is the water which you are seeing here, river, and this is how the quartz reefs are looking. Now, you can also do a land use analysis, that which type of lands will get inundated if a reservoir is constructed. All things are modeled. Everything is being simulated before an appropriate decision is taken. So, immediately implying the satellite images, current land use can be assessed, land cover land use can also be assessed, as has been done for this case. And if you are having revenue record and put this polygon, this is the inundated area of the reservoir, immediately you would know that whose land will be submerged. So, if it is acceptable to local people and decision makers, a reservoir can come. In 2 years time, it will start providing benefits. So, what are the possibilities? That identification of suitable sites for water harvesting has been made very easy using GIS or geoinformatics technology. Preliminary assessment can be done. For detailed project report, obviously things have to be checked on the ground, but feasibility studies can be done very easily, and different scenarios, different options can be created for better decisions. And simple solutions, this is my whole point of discussion, is what solutions which I am providing are very simple and implement with the local people and local material. Even if you imply a Google Earth image and a Google Map image, you can see these quartz reefs very clearly on that, because in the Google Map you are also having digital elevation model, and that is in the shaded form, that is a hillside. So, these things can be identified, water bodies are also shown there. So, data is available. See here, like the quartz reef is running like this, river is moving like this, going like this, only thing we require to block this one to make a reservoir like this. So, this is one option. Another thing is how to further assess this situation, and that you remember that we did a hydrologic modeling in GIS, and we created a drainage network. And while discussing this surface hydrologic modeling, in the beginning I said there is an assumption that each drop of water will flow as a surface runoff on the surface. So, that assumption is okay, we can exploit even that assumption and can find out just without doing much and just adding one more layer, and can find out which are the areas which will provide better groundwater recharge. So, basically we have to compare a simulated drainage versus surveyed drainage. Surveyed drainage, that is the real one which can come from survey toposheets, and we can get an insight about groundwater recharge. So, I am this part we have already discussed in surface hydrologic modeling, that you use a DEM, you fill it, flow direction, flow accumulation, thresholding, stream network and stream order. So, once that is you are then having in your system, you also require a surveyed drainage network, and that means the digitizing the whatever the best scale toposheets available for a particular area. And if when you overlay these things, you would notice that in some parts the surveyed drainage and model drainage are almost same. But when you would further observe in some areas, like here in this lower part, that the surveyed drainage and model drainage, there is no match. That means that the model drainage is in the assumption that the model drainage and the water has to flow. So, there is a deviation, and a deviation in the position of the drainage network, because natural drainage where whatever the water going towards groundwater regime, that will affect the drainage system. So, this mismatch we can exploit, and we can say just comparing these two networks, one is modeled one, another one is the real one, that wherever the mismatch, we are having high chance of getting groundwater one, and these are the areas where groundwater recharge structure should be constructed, because the surveyed or real drainage is not following the modeled drainage concept. And if it is following, that means whenever both are coinciding, that means surveyed drainage and model drainage are same, that means there is no loss of water, assuming that entire watershed is having same evapotranspiration losses. So, other losses are to the groundwater. If there is a loss to the groundwater, then definitely the model drainage will not follow the surveyed drainage, and this mismatch can also be exploited. So, very simple technique. One more example of a different area, you can see it works very well. Of course, you can find out the areas which are good for artificial recharge groundwater regime, that you can do it quite easily. Similarly, you can find out the potential groundwater recharge zones for another basin. So, what we see that by developing this benefit versus submerged area ratio for the different region of the country, if we are having beforehand, we would know that if a structure is created, how much benefits in terms of this benefit area I will going to have, what is the return I am going to, because decision makers would like to know that okay fine, if I construct a reservoir here, how many years it would take, what the benefits it will provide. All these answers, all these questions can be answered through such analysis. So, with this basically identification of suitable sites for water harvesting I have already discussed, and preliminary assessment can be done. Of course, if before construction a detailed project report has to be prepared, no matter how small the reservoir is, and then construction can. And these are a small check dams kind of scenario. So, you do not require many decades to construct a reservoir, just one season or two seasons or 1 year or 6 months, within that employing the local material, employing the local people, one can construct such check dams, and not only one, but in cascading if it is possible, on the same stream multiple. So, tail of one reservoir ends, another should start, because we want to hold or delay the rainwater as much as possible. So, simple solutions with local people and local material is possible. So, with this I end this discussion, that just recall we started with dam simulations. Just using those dam simulations for at least for hard rock terrain, we can find out the best suitable sites for groundwater recharge, and if those sites are developed in 2 or 3 years time, we can start seeing benefits. You can verify your ground truth, or you can verify or validate using satellite images which are having unbiased recordings, and you can also tell that only it will take 1 or 2 years time to have or to see the benefits. How much area it will come, that can also be predicted. So with this, I end this discussion. Thank you very much.